So this video covers the material in section 10.3. I'll do section 10.4 as a separate video, maybe several separate videos. But this all goes with the same set of PowerPoints that you're looking at, section 10.3 and 10.4, displaying data. This is actually 10.3, and then measures essential tendency is a very long section 10.4, which is split into many days. So section 10.3 starts with the second part of displaying data. We already did some of the stuff in class with pie charts and graphs and histograms and all that kind of stuff. So this is talking about the difference between a discrete variable and a continuous variable. Discrete variables are individual. They're whole numbers of items. So I listed them as variables whose possible values can be listed. Things like children, cars. If you were counting number of cars that came into the parking lot during a certain hour, they would be a discrete number of cars. It would be 52. It would be 43. It wouldn't be 17 3/4 cars, even if you're missing one of your taillights and a door. It's still a car. Same thing with textbooks. Parking spaces, no fractions. Continuous variables form an interval of numbers. So things like temperature. The temperature of the day doesn't only exist in whole number increments. Today's high temperature could be 32.7 degrees. You could travel 114.753 miles. So those are things that don't come only in whole numbers. They come in fractions and decimals as well, and so we call those things continuous variables. So if something is discrete, you're going to have a bunch of little dots on your graph. If something is continuous, you can connect it with a line or a curve or whatever else makes sense for your particular problem. So continuous data, here's an example. If you monitored somebody's weight over 10 years, you don't know 100% certainty that it goes by this line. Probably the doctor's office is going to weigh them at their annual checkup. So you know what they weigh at year 0, and then at year 1, and then at year 2, and then 3, and then 4, and then so forth. But you don't know necessarily that it follows this exact pattern in the middle, right? Maybe they gained a bunch of weight, and then it leveled off, and then it went under, and then it went up again. So it is possible that between a year and 2 years, it actually went more like this. But we're probably pretty convinced that the weight followed a similar pattern where it went from 1 year to 2 years to 3 years to 4 years. And so you connect the dots with little segments because you realize that it didn't just happen once, right? They didn't gain all their weight for the year at one time, even though some days it feels like we might be able to. But no, little kids don't do that, right? They gain a little bit of weight, they gain some, they lose some. So over the course of a year, it's reasonable to connect the segments. So this is the person's weight over the course of 10 years. Here's another graph. This one maps the temperature each hour in Salt Lake City, Utah on a particular day in July. Now, notice that they labeled the axes for us, right? The vertical axis, oftentimes we call this the y-axis, is the temperature. It tells us that it's in degrees Fahrenheit. And we notice this little mark down the bottom that indicates that we're not starting at 0. It makes more sense for our graph to start at 50 because there weren't any temperatures that were less than 50. So to make us aware that we've skipped some values, they put that little funky mark in there. Hours 0 through 25, so you can see it stops at 24 hours in a day. You realize at the beginning of a day, the temperature actually drops from about midnight to 6 a.m. So here it is dropping from 70 down to 58 maybe, and then the temperature begins to increase. That red dot looks like the temperature at 8 a.m., so at 8 a.m., the temperature was about 70 degrees. Then it begins to increase. Where does it hit its maximum? Not at noon, at about 3 in the afternoon, 3 or 4 in the afternoon. Right, that looks like where the peak is. Then it starts to come down, and by midnight, it's about where it was at the beginning of the previous day. So it warmed up a little bit throughout the course of the day, right? This looks like about 70. Maybe this temperature over here looks like about 72, 74. But it's ended about where it started. But it went down. It went up, and it went back down again. And again, do I know that the temperature increased exactly at this rate between hour 7 and hour 8? No, but if I know where it is at 7 o'clock and I know where it is at 8 o'clock, temperature is not a discrete term. It increases, or decreases constantly, so we would say it's a continuous variable. All right, so scatter plots help us to see a trend. What you do is you plot all the XY pairs, and then sometimes you can draw a line that goes through every point. If it's an exact thing, like if you're traveling at exactly 40 miles an hour, you'll have hour 0 times hour 0 distance 0, hour 1 time 40, hour 2 time 80, hour 3 120 miles, hour 4 160 miles, and so forth. So the distance you travel will always be 40 times the number of hours that you traveled. You can model it by other lines. The little plot that I gave you up here is modeled by more of a curve that seems to be periodic. It goes up and then down. If we continue this, it would go down and then up and then down. So that's something that's not modeled by a line, right? It's modeled by something more like a curve. All right, so we'll look a little bit at sequences, and then we'll come back to the idea of those scatter plots. So suppose I have a sequence whose first term is 11. Every term after that is 3 less than the previous term. So what if we made ourselves a little table of what the first few terms look like? So I'm going to call this term number n, and my term itself will be a sub n. So term number 1 we said was 11. Every term after it is 3 less than the previous term. So term 2 is 3 less than 11, so it's 8. Term 3 is 3 less than that, so it's 5. Term 4 is going to be 2. Term 5 is going to be 3 less than 2, so negative 1. For sequences, we plot these as discrete terms because there is no term 1.5. There is no term 3 2/3. It's term 1, term 2, term 3, and so forth. So this is n. This is a sub n. So what should I go up by? May I go up by 2? As I realize I'm not graphing this on a piece of graph paper, so it's not going to be the world's best graph, but it wouldn't be any better if I were graphing it on a whiteboard in front of a classroom. So here's term 1, term number 2, term number 3, term number 4, term number 5. So term number 1 we said was 11. So I go over to 1, right? I start at the origin, I go over to 1. And then halfway between 10 and 11, it's a good spot to make a dot over there. Term number 2 is 8. Term number 3 is 5. Okay, term number 4 is 2. Term number 5 is below the axis. That's negative 1. So my sequence is graphed like this. Suppose I want to put a trend line in there. If I had a nice ruler, could I make all these points fit on the same line? Sure. Let's see if I can do it without a ruler. That's the real test. All right. So if I actually had a ruler, these things would all fit on the same line. Can I make a formula for this? Sure. We've done this a couple of times. The nth term is the first term plus n minus 1 times the constant difference. If you didn't take 107, you haven't seen this formula before, that's fine. This is basically point slope form for a line, but applied to a sequence. So A1 is the first term. D is the constant difference between the terms, which in this case is negative 3 because it's always going down by 3. How do I get from one term to the next term? Subtract 3. So the nth term is the first term plus n minus 1 times negative 3. Let's simplify that. Negative 3 times n is negative 3n. Negative 3 times negative 1 is positive 3. And so you get an equals negative 3n plus 14. So do you see my graph? The way I graphed it was a little bit below where it should have been, right? It should have been up a little bit higher. And so if I'd actually graphed it more like that, then it should cross here at 14. All right, so this is a sequence that starts at 11, and every term after that is 3 less than the previous term. So we drew what we call a trend line. Okay, your book calls it a trend line. Sometimes we call it the line of best fit. That goes through as many points as possible, but doesn't necessarily go through all of them. And there are cases where the line of best fit doesn't go through any of them. In this case, it went through all of them. Why? Because it was a formula, so it had to fit that pattern. Not all of them do. All right, so here's an example of a scatter plot. When we read a scatter plot, we take a look at the axes, we take a look at the units, we take a look at the scale, and see what information it has for us. So notice that the title says quiz score results. Okay, so this is a result of a quiz somebody took, or a lot of people took. Down here on this axis is number of hours that they studied. On the vertical axis is their score on the quiz. It says the highest score is a 10, the lowest score was a 1. Nobody got a 0. If you look down here, these people both got a 1 out of 10, and they studied different amounts of time. Here are 5 people that all studied 5 hours and got 5 different scores. They got a 3, a 4, a 5, a 6, and a 7. But in general, if you look at the way this thing is trending, it looks like the more hours you study, the higher your quiz score is. Is it universal? Like, is it guaranteed that the more hours you study, the higher your quiz score is? No, because look at these 5 people that all studied 5 hours. They all got 5 different scores on the quiz. Right? Here's somebody that studied 3 hours and got a 3 out of 10. This person studied 4 hours and only got a 1 out of 10. So it's not perfect. It's not guaranteed that it'll always work like that, but that is the trend. So I can't see, this is not a tablet that I'm writing on. It's actually like a tablet pad. So I'm going to give it my best shot to draw a trend line. Right? Maybe something that looks like that. So you notice that the line doesn't go through every point. Maybe it only actually hits a couple of the points. But it looks like I can find a general pattern. And then if I wanted to, I could find a couple of points on there and calculate the slope to see, like, for every hour that I study, is that another 10% that I get on the quiz? Is it 5%? Is it 8%? You know, in general, if I study X number of hours additional, how much more would I expect to get on my test grade? So I've drawn my scatter plotter. It was already drawn for me. And then I added the trend line, or the line of best fit. You can see that it has a positive slope. So it looks like as the number of hours increases that you study, your score on the quiz will increase as well. Okay, so this is one that was drawn in by the textbook that I used. You can use it to make predictions. So you're taking this discrete data, right? They ran into the whole number of hours, and you say, well, what if I studied 1.5 hours? Then I might expect to get that score over there. What if I studied 5.25 hours? I would expect to get this score over here. All right, so you can make predictions. So here's another set of data. Relationship between number of absences and a final grade. And this one actually asked me to give the association and then use 2 points to find the equation of the trend line. All right, so I've given you a nice blank grid. You notice I mostly gave you just the first quadrant because there's no negative number of absences and there's no negative grades. This one specifies, put number of absences on the x-axis and final grade on the y-axis. Now, let's think about what kind of numbers we have. The absences go from 0 to 12. So maybe I'll make every line worth 1. 1 absence, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so there's my scale for number of absences. Each of those grid lines are a point on my scale. And then for grade, looks like 65 is the lowest. So can I do one of these things where I show that there's a break? And then that's 65, 70, 75, 80, 85, 90, 95, 100. How did I do that? I literally eyeballed it. I didn't plan in advance how I was going to do that, but I said, look, here's 65. I got a bunch of dashes. I want to go to 100. If I make each one worth like 5, it's going to squish the graph all the way down the bottom. So why not try for 2? This pen is erasable. If this didn't work, I could always erase it and try something else. The other thing I could do is I could actually sit there and count the number of grid lines, count out how many grades I need to include there, and then just divide through to find the optimal scale. But you should try to spread this out a little bit on the graph so it's not all stuck in the corner. All right, so let's graph. 10 absences, person got a 70 for the final grade. So I come over to 10 up to 70. So if you look at the 10 and the 70, that's where those two things overlap. All right, the person who had 12 absences got a 65. 12 absences, 65. Person who got 2 absences got a 96. The person who had no absences got a 94. The person who got 8 absences got a 75. And 5 absences, 82. All right, so except for that little blip up at the top, it looks like as the number of absences increase, the grade decreases. Let's pick 2 points and make an equation for the line. Okay, which 2 points should I pick? I don't know. These look like reasonable points to pick. So which ones are these? 582, right? So that's one of the 2 points. And the other one was the one with the 8. Okay, so they're underneath each other on my table. Nice. First thing I need is a slope. So slope is change in y over change in x. So 82 minus 75, that's my change in y. 5 minus 8, that's my change in x. So 7 on the top, negative 3 on the bottom. Not surprising that the slope is negative because we said as the absences increase, the grade decreases, so the slope should be negative. Next thing is equation for the line. I'm going to go with point slope for a line, so y minus the y coordinate equals the slope times x minus the x coordinate. I can pick either point. I don't know. I'll pick the 5 and 82. So y minus 82 equals negative 7/3 times x minus 5. All right, let's distribute. So y minus 82 equals negative 7/3 x plus 35/3, right? Distributed negative 7 times negative 5 gives me positive 35 over 3. And then my last step is simply to add an 82 to both sides. When I add an 82 to both sides, maybe I should add it as a fraction of 3. Here, let's grab a calculator and multiply 82 times 3. 246. So 246 thirds is the same thing as 82. So I'm going to add an 82 to both sides. And I get y equals negative 7/3 x plus 246 plus 35 gives me 281. All right, what is 281 divided by 3? It's 93 2/3. So here's the equation for my line. Now, what could you do with that line? Because if I drew it in, it would look like this, right? Down here, it might be above a couple and below a couple. After a while, you're going to need either more of your graph or just sort of an end to it, because you realize that I cut out a bunch of values by putting that little mark over here. Well, now if I want to make a prediction for what happens if somebody has 15 absences, they didn't have a negative grade, their answer is buried somewhere in there. So if I wanted like 14 or 15 absences, I can just put a 14 or 15 in here for x and see overall what they get. All right, you notice the trend line doesn't go through these 2 points up here. Is that okay? Yep, that's okay. This is somebody that was absent a couple of times and still got a 96. This guy was not absent at all and got a 94. But in general, you can see from the points down here that that trend line fits pretty well. Okay. Sometimes we call these things a correlation. How are they correlated? That as the number of absences increases, the grade decreases. Now, correlation is a type of association. Correlation and causation are not the same thing. There are ways to find out if there is causation, but that's sort of a hard thing to prove. Like I notice that there's a trend. As the number of absences increase, the grade decreases. But is the grade decreasing because of the number of absences? That's something that's trickier to prove. It looks like they're related to each other in that way, but just because they're related to each other doesn't mean that one causes the other. So a positive correlation would look like this. Essentially, it's a positive slope. You've got a whole bunch of dots that you've plotted on your scatter plot. As the x's increase, so do the y's. Negative correlation looks like this. As the x's increase, the y's decrease. So as the temperatures increase, the layer of clothing that you wear outside decreases, right? Negative correlation. Doesn't mean it's a bad thing, right? That means the weather's getting nicer and we can get rid of our winter jackets. But the correlation is negative because as one increases, the other decreases. This third thing over here is a case of no association. So you notice in the first couple, a lot of the points clustered around a line and in a certain direction. It is possible that you graph something with no association at all. Like if you graphed test scores versus eye color or something like that. I'll bet there's no correlation between people with certain eye color and getting higher or lower test scores. So something like that probably has absolutely no correlation at all, right? The house number that you live in versus your test grade. So people with higher house numbers, do they have higher test grades? I'll bet you there's no association at all, right? It's a completely random thing to look for. So you may think something is correlated, and then you go to graph it and realize you get one of those graphs like the third one that just has no correlation. All right, my other example about correlation and causation. Just because it's correlated doesn't mean that one causes the other. The classic example is in New York City. As the number of ice cream sales increase, so do the number of emergency room visits. So if you graphed it, you would almost go, oh my goodness, ice cream must be causing people to go to the emergency room. But could there be another cause to it? Well, what about the idea that ice cream is generally sold when it's warm outside, and people might be going to the hospital with heat exhaustion or heat stroke or something like that? So just because ice cream sales increase and emergency room visits increase doesn't mean that they're going to the emergency room from eating ice cream. Right? There could be a third thing in there that we're not looking at, and that's why we say that there is a correlation, but there's not causation. All right, I'm going to skip the example with the coffee makers. You can graph these things by doing what? By putting the dollars on the x-axis and the rating on the y-axis. The question is, does a more expensive coffee pot guarantee that you're going to get a better cup of coffee, or is there no correlation at all, or is it weak? Is it, well, sometimes it works, sometimes it doesn't type of thing. All right, this is the last thing for this video and for this section. I just wanted to point this out. It is possible to have a graph that has multiple line graphs on the same graph. So this is an example showing the crowdedness of housing from 1940 to 2000, meaning how many people were living in a fixed amount of square feet. So more than one person per room. Severely crowded is more than 1.5 people per room. So the blue dots are the severely crowded. So that's the 1.5 people on average per room. The red is just crowded. You can see that they start and end at different places. They never actually cross each other. They get closer as the years go by. But you also notice that they trend in the same direction, right? Housing in 1940 was very crowded. The suburban boom and all that, by 1980, they had both dropped, and then they began to pick up again between 1980 and 2000, but never back to the levels that they were back in 1940. So it is possible to compare more than one thing at the same time using what they call multiple line graphs. All right, and that's it for this video.